Facts highlighted viewers, welcome. Most of us hear the word nuclear and imagine nuclear bombs, destruction, and nuclear waste. But what if I told you all that's about to change? Imagine a reality where the world is powered by limitless clean energy, no carbon emissions, and virtually no radioactive waste. This utopian energy source has been the pipe dream of scientists for decades. And enter nuclear fusion. With the promise to stop carbon emissions, produce clean, abundant energy, transforming the entire energy landscape for the planet forever. Let's get into it. Nuclear has always been a real problem child, dividing public opinion nearly in half since its inception. It has been the source of conflicts, protests, wars, and worries for governments and policymakers for years. The only time nuclear weapons were directly used on a population resulted in an almost immediate genocide. The US atomic bombings in August of 1945 killed over 150,000 people in Hiroshima and up to 80,000 in Nagasaki by year's end. Chernobyl in northern Ukraine near Pripyat, on the border with Belarus, houses a reactor which melted down, causing a massive explosion, releasing radioactive material that blanketed Europe. It was caused by a flawed reactor, human error, and a lack of safety systems. The impacts were wide-ranging. It caused 30 immediate deaths and a displacement of hundreds of thousands of people and an exclusion zone of 30 kilometers, aside from hundreds of cancer patients, which resulted in global policy shift. Fukushima-shi, located in northeastern Japan on Honshu, Japan's largest island, which was the home of Daiichi nuclear power plant, which was struck by a 9.0 magnitude earthquake in 2011, which triggered a tsunami, flooding the reactors and backup generators. This led to 3 of the 4 cores melting down, resulting in huge explosions and hundreds of thousands needing to be evacuated. But this is where there is some new hope. Clean, abundant energy has always been the goal of energy scientists for decades, but nuclear fusion has always been 20 or 50 years away, but never any sooner. As we speak, all that is changing with competition from 45 companies and the likes of the ITER program involving thousands of experts, 35 countries, and tens of billions of dollars. Our parents and grandparents were fortunate to have witnessed the launch of astronauts into space and the first steps on the moon. And we may just see the recreation of the sun and stars right here on Earth in our lifetime. Nuclear fusion energy currently supplies between 9 and 10% of the world's electricity reliably. They are fueled primarily by uranium. They generate energy by splitting uranium atoms in a process called fission. This splitting releases a large amount of heat, which is then used to produce steam that drives a turbine to generate electricity. An analogy would be if we take a log of wood, split it, burn it, and release the energy within. This is similar to the splitting of atoms in fission. Fusion, on the other hand, is the opposite nuclear reaction. It's a process where fusing 2 light nuclei to form a heavier one and releasing the energy. So, for example, if we take 2 magnets and join them at the same pole, so magnets have a north and south pole. If we were to try and join magnets at the north pole, they will repel. So we have to try and join them, weld them, and form a heavier magnet. So fusion is very similar. Since the 1950s, we have been conducting experiments in the US and Soviet Union who approached the same problem slightly differently, the US with the stellarator and the Soviet Union with the tokamak. Forcing atoms together require huge amounts of energy, trying to force 2 atoms to fuse that don't want to form a heavier element. And to do this, a plasma has to be created, which is a cloud of charged ions, and due to this charge can be manipulated by a magnetic field. This is so the plasma doesn't melt the walls of the reactor, which at this stage is millions of degrees, and no known solid matter in the universe is able to withstand these temperatures. When the temperature is raised, it causes these ions to speed up so high, which enables them to push through the electromagnetic barrier, which then causes collision and then fusion. Both stellarator and tokamak can fuse atoms, but due to a much higher efficiency, the tokamak is the leading design. Both employ the same fuel, however, the exact reactants used has a huge effect on the amount of energy that's got to be input into the reaction. Fusion can be achieved with regular hydrogen, but the energy output is extremely low, so we combine two heavier elements, deuterium and tritium. Deuterium-2H and tritium-3H, which provides us the largest possibility of fusion or the reaction that's necessary. Fusing hydrogen has a high possibility of producing helium-2, which due to its instability decays immediately into two regular hydrogen atoms, releasing a small amount of energy and much lower probability of combining and forming deuterium-2H and the desired reaction, which then fuses to form tritium or helium-3 and then decays into helium-4, the reaction powering the sun and stars. Using deuterium and tritium instead of hydrogen-1 dramatically increases the probability of causing helium-4, which on average releases 17.6 mega-electron volts for every fusion reaction, which compared to uranium produces 200 mega-electron volts, which is overall 11 times more energy. But as a whole, fusion promises to produce 4 times more energy, but with almost no nuclear waste and helium as a byproduct, which is quite useful in various applications besides the obvious of floating balloon or the Mickey Mouse voice, such as cooling MRI superconducting magnets, the cooling of some cores in nuclear reactors like the one initiated in South Africa, and to prevent rockets from exploding by filling the tanks after propellant has been depleted. And there is more good news. Deuterium can be found abundantly as it naturally occurs in seawater and makes up 0.02% of all ocean water on Earth, giving us a reliable source for generations. Tritium, on the other hand, is a bit of an issue with global reserves at around 20 kilograms, which means the ITER program alone in the south of France will burn through the entire global reserve in just over 2 months. However, nuclear plants produce it, but at a mere 100 grams per year. We discovered if we add lithium to the fusion reaction, it splits into tritium and helium, which occurs in a blanket around the fusion chamber. The blanket has a few tasks that it must achieve besides produce tritium. The majority, over 80% of deuterium and tritium reaction is carried off as kinetic energy via neutrons, and this has to be harnessed and converted into electricity. Tokamaks achieve this by slowing down the neutrons in the blanket, using atoms to trade their kinetic energy for heat, which can then create steam, turn a turbine, and produce electricity, and voila, the sun on Earth. Fusion is fundamentally simple, but it is an incredibly complex reaction to implement. Fusion reaction needs 100 to 150 million degrees Celsius compared to the sun's core at just 15 million, due to the plasma density in the sun's core, which has 150 times the density of water, coupled with enormous pressure which overcomes nuclear repulsion. The sheer number of atoms in the sun renders the probability issue irrelevant. A host of countries and companies and many big names have thrown their hats in the ring. ITER, the International Thermonuclear Experimental Reactor, is the world's largest nuclear fusion project currently under construction in southern France. It's a multinational collaboration involving 35 countries, including the European Union, the United States, China, India, Japan, Russia, and South Korea, aimed at demonstrating the feasibility of fusion as a large-scale carbon-free energy source. Once operational, ITER aims to produce 10 times more energy than it consumes, generating 500 megawatts of power from 50 megawatts of input. ITER is supposed to have its first plasma event in 2022, but it is now scheduled for 2027 due to construction delays. with deuterium-deuterium fusion reaction in 2035 and deuterium-tritium fusion reaction in 2039. The UK government is building one of the largest nuclear reactors ever constructed, known as Hinkley Point C. And after its completion, they're planning on building Sizewell C in Suffolk and has signed a deal with the US for 12 SMRs or small modular nuclear reactors powering data centers. So fission isn't going away anytime soon. Neither is its waste, with a half-life of 4.5 billion years. And there's a lot of it. Wars today are mainly fought for control, territory, and energy, and this will probably not entirely stop. But with a sustainable, robust, cheap, and accessible abundant energy source, warfare, for the most part, may be stopped, and ultimately transform our lives and the world over. The energy grid is a complex machine, and one source may not be our Achilles heel. We have an ever-increasing global energy demand from electric vehicles, developing countries, and data centers. So one source may not be sufficient. Policymakers and leaders today can only make decisions that majority of us are fine with or willing to let slide. That is why all of us collectively got to push our governments to enable all energy research to transform the fossil fuel-driven energy mix we have today, building a better future for all of us. If you've made it this far in the video, please do consider smashing that like button, hitting subscribe, and take a moment to leave us a comment or suggestion for any future or upcoming videos. And thank you for watching.